All right, good evening. So we're back to checking out, ready to learn things. So we looked at these top four last time. Okay. And now we're just going to go ahead and hit the next thing here. Okay. So we have multiplicative property of equality with sign fractions. Let's see what that looks like. Okay. So we have negative 12 is equal to 2/5 of u. Okay, so how do you solve something like that? I think we haven't kind of taken this for granted that you guys could do this, but here we go. So hopefully, if you already know, that's great, and if you don't know, well, let's see if we can't fill in some holes here. So all we're trying to do here is we have to isolate this. So all we're going to do is multiply by the reciprocal. So the 5s will cancel and the 2s will cancel, and that's really all we're doing here. Now, on this other side, we could be clever, but you don't have to be. If you forgot, that's okay. You just say, well, 12 times 5, that's 60 divided by 2, and then we can go ahead and reduce this and get 30. So wait a minute, I thought we could reduce early. Like, you'd be right. You could also reduce early. So you could take this 2 and make that a 6, and you're still going to get, right, u is equal to negative 30. So it works either way. So if you weren't paying attention in the middle of it, and you say, oh, I forgot I could reduce. Like, well, then you can do it later, and it's fine. All right? It doesn't matter. Let's do one more. Let's see if we can find a. Oh, okay, I see. They have they span the gauntlet from A to A. Okay, this one looks pretty good. So we have 5/8 times x, and that is equal to negative 10. So again, same process here, right? We're just going to multiply by the reciprocal on both sides. Okay, the 5s cancel, the 8s cancel, you have x. And then still, right, if you think, oh, I could just do this, you're absolutely right, you can do that. Okay, so we'd end up with negative 16. If you forgot, then you'd have x is equal to negative 80/5, which should strike you as suspicious, and end up with negative 16 anyway. Okay, so that's what we're doing with those. So that's not too bad. Okay, so fractions. Let's go ahead and mix this. Okay, so this one might be fun because there's going to be a whole bunch of knots to untie here. So let's see if this does anything more for us here. So solving linear equation. Okay. Oh, how terrible does that look, right? It's enough to strike fear in anybody's heart. Okay, so I'm going to go ahead and write the things with the variables on the left and the thing without the variables on the right, only because that's usually how I'm used to solving these. Now, we have some choices, right? And one of the choices is getting common denominators between the two of these, because when you have to add fractions, that's kind of a pain. You want to multiply fractions, you're fine. But you want to add fractions, we have to get what they call common denominators. So I'll call that method 1 of finding a common denominator. And adding before we solve the problem. But there's another method. Okay, so I just want to let you know there's several ways to pull this thing apart depending on how you want to do it. Okay, so the first way, we're going to look at this and I'm going to say, I'd like this to be a 4 down here, right, or an 8 down here. Right? We have a 2. How do I turn that into an 8? It's W minus 9. Let's multiply by 1. Right? That's 4/4. That's just 1. I don't have to do anything with this guy over here. Just going to leave it. So we're going to have W plus 4 all over 8. Now this bottom part is going to be an 8. But this top part, right, we got to distribute this top part. So that's going to be a 4W. And then 9 times 4, that's going to be a minus 36. Okay, so we have 4w minus 36. We're just going to leave this alone as a 1. Okay. So now they have common denominators. We can add these. So we have 4w's plus 1w. That would be 5w. We have a negative 36 plus 4, right? That's going to be a minus 32. And this is all over 8. All right. Now, what did we do in the previous one? Right? In the previous one, we multiplied by the reciprocal of the thing in front of the x. So we're not really going to multiply by the reciprocal because this is complicated. But if I just multiply by 8 over 1, won't these guys cancel? And the thing is, if you do it this way, this will cancel for both of these terms. Okay, that's how fractions work. So we're going to end up with a 5w minus 32. Okay, they both canceled. And this is equal, 8 times 1 is 8. Okay, and now we can go through, there's a lot of 8s in this. So we have 5w. We're going to add to both sides, right? 32 plus 32. And that's going to be 40. And then finally, divide both sides by 5, divide both sides by 5. And we end up with w is equal to 8. All right. What if you said, you know, I think that was quite a lot. And I really don't want to find a common denominator. I don't like the fractions. I'd like to remove them as soon as possible. Okay, let's do it that way. So this is a different method. Okay, it's the same method, but it does it in a little bit of a different order. But as long as we track through it, it'll be fine. Okay, so what I want to do is I want to multiply both sides. They got to be the same thing. Okay, if I multiply by 3 over here, I got to do 3 over here. 3 ain't going to help. So I'd like to multiply both sides by something that's going to remove both of these fractions. Now, if you wanted to do 16, that's okay. It'll still work. Okay, but it does make it a little bit bigger than you'd really want. A number that's going to remove both of these fractions would be 8. 8. Okay, and then we have to distribute this 8 to each of these terms. All right, so we have 8 times w plus 4 divided by 8. And now we have 8w minus 9 divided by 2 is equal to 8. All right, so remember, it's got to go to both. Don't get excited because you did the first one and forget the second one. All right, it doesn't work that way. And you have to be consistent on both sides. So 8 over 8, that's just, right, that's the whole point. We just have w plus 4 because these guys canceled. Now for this one, right, we're going to need like a little intermediate step here. So 8 divided by 2, that's 4. So we're going to have a plus 4 w minus 9, and then go back to equals 8. Right? Right. And then we can solve this just the way we did in the previous one. Okay, so we're going to have a w plus 4 plus 4w. Don't forget the other one, minus 36 is equal to 8. So that's going to be w, 4w's plus 5, 4w's plus 1w is 5w. That's going to be 4 minus 36, it's going to be minus 32, is equal to 8. And at this point, right, you can see that this problem here was the same as this problem up here. Okay, so we'll continue working with it. Right, so we have that. So we have 5w, 8 plus 32 is 40. And then divide both sides by 5, divide both sides by 5. And we have w is equal to 8. All right. Now, of the two methods, I'm usually interested in using this method. Effectively, they are the same thing, but I remember having so many difficult times with fractions when I was learning them that if I can avoid the situation, I would prefer to do that. So the sooner I can get rid of this as a fraction and get it to be like regular whole numbers here, the happier I am about the situation. So my preference is always to do this, but there's other ways to think about it, and that's fine. Okay. So should we do another one of those? Maybe we should do one more. Hopefully they give me a different, oh, that one's beautiful. That was a mess. Okay. So let's have a look through at this one. Okay. We've got x plus 5 divided by 7 minus, oh, there's lots of things going on here. 7x minus 5 all over 3 is equal to -2. All right. So in this case, right, I'm going to solve it with the second method, if that's okay. In this case, I need a number that's going to clear both of these fractions on the left side, and I don't really care what happens on the right. As long as we're consistent in carrying it forward, we'll be fine. Now, in the last problem, when I multiplied by 8, it got rid of both of these. But if I put a 7 here, this 7 over 3, that isn't helping. So I think we're stuck with trying to multiply these two together. And we're going to multiply and get 21 here, 21 here. All right. So let me write 21 as 7 times 3. Okay, just for a moment. What happens, right? We've got 7 times 3 times, that's my here, I'm sorry. All right, so we have 7x minus 5 over 3 here equals, and that's just -2 times 21. I think that's -42. Yeah. All right. So the reason I wrote it this way is because I really wanted you to be able to see like what's canceling here. Okay, what's canceling? So we could look at this and we could say, hey, wait a minute, there's the 7s and those both go away. There are the 3s and those both go away. Now you're still left with something, so you still have to distribute this. All right, so that, you have to be careful and make sure you're doing this like one thing at a time, because it's really easy to lose these pieces. So this is now 3 times x plus 5 minus 7 times 7x minus 5, and that's equal to -42. Okay. The 3's canceled, the 7 remains. Oh, in this one, the 7's canceled, the 3 remained. Okay. And now we just have to go through and untangle all of this here. Okay, so that's going to be 3x plus 15 minus 49x. Don't forget the minus times the minus, and we'll have a plus 35 here, and that's equal to -42. Okay, so there's a lot to keep track of, but that's okay, we can do it. And now we're going to go ahead and say minus 15, minus 15, minus 35, minus 35. And what do we have left here? We have 3 minus 49, right? And that's going to be a -46x, right? You have $3, you spend $49, now you're in debt. Congratulations. This one, what is this going to be? It's going to be 4. This is going to be 50. Looks like 92, right? Making it 92 here. All right. It's almost done. Just going to divide both sides by -46. Divide both sides by -46. And I believe we're going to get x by itself. Negative on negative, that'll cancel. And I believe 2 times 46 will give me 92. So we're just going to end up with a 2 here. Right? And then you're done. You're solved. Okay. So I think that's a good one to go with. Okay. It was solving a linear equation with several variables. Oops. All right. So what are we looking at next here? We have sine fractions, fractional forms with binomial numerators. Let's go with algebraic symbol manipulation type 1. Names they come up with for these. Okay. Oh, okay, that's all they want us to do here. So solve this for y. Okay. This is kind of what we did yesterday, right? With the ordered pairs. All right. So let's go ahead and add the 3x to both sides to get the y by itself on one side. So we have 2y is equal to 3x plus 17. Does it matter which side I write these on? If I do this, we're going to get 9, or sorry, we're going to get 9 either way. Yeah, it's okay. So it doesn't really matter how you've done this, right? You could say I've got $3 plus 17. I don't think I can make a euro sign. That's not it. How about 17 yen? I can make that sign. Okay. Well, that would be the same thing, right? I'd have 17 yen plus $3. We wouldn't care. So we could swap around. And then what we're going to do is we're going to get this by itself. Okay? So we just untangled a binomial thing. Now we're going to tangle one up. So what we're going to do here is we're going to divide by 2. We're going to divide by 2. All right. So you get y is equal to, I don't know if it'll let us do it this way. We might have to break apart. Okay. Now the tops you can break apart. The bottoms you can't, but the top you can break apart. And the idea is here, if I'm going to go off and do laundry, I've got 4 quarters, right? I could put 1 quarter in one pocket and 3 quarters in another pocket. And I still have the right amount of money. So the tops, you can break these up, right? You can put your quarters in different pockets. The bottoms, let's see what happens, right? This is 4 over 4. Remember, I started with $1. So can we do this? Could I say this is, the state is a 4. So can I break it up like this? So this would mean I have $1, and then we're going to turn it into $4 plus 1 1/3 dollars. Like that ain't gonna work. Okay, so don't try to do that. Even if I change these, it still isn't gonna work, right? I still have $2 plus 2/3 of a dollar. Like either way, just put my money in different pockets means I'd have more of it, which would be great, but that's not how that's gonna work. So the tops you can take apart and move where you want, but the bottom has to stay the same, right? No matter what we're doing, I got 4 quarters. And I can move them into different pockets, but I still got a bunch of quarters. The top, if you try to break up the bottom like that, it's saying I don't have quarters anymore, and that just doesn't work. So don't do that. This is the way it works. So with that being said, you can break this around and say this is 3x over 2 plus 17 over 2, and that's equal to y. So I'm not entirely sure about what format they're going to want this in. Hopefully they'll let you get away with this. So that's right. But they might insist on you breaking this down all the way. Okay, so be careful about that and just realize, like, when you're dealing with your fractions, you can break apart the tops, you cannot break apart the bottoms. All right. All right. So let's go ahead and get on to some of the stuff we're supposed to be doing today. Okay. So let me see here. All right. So we were looking at domain and interval notation and writing some other stuff down here. So there's the last couple of few problems out of this section, but let's make sure we did the hard ones, right? So that you guys, when you go to do this, you're going to be able to say, oh, I know what I'm doing here. Okay, so interval notation, right, doesn't include the number. That's a terrible, my handwriting is the worst. I have arguments all the time with people about whether or not we should learn cursive anymore. Cursive was invented to deal with pens that were not so good. So, but this does not include. All right, so if I want to put in like the interval 1 through 8, what this means in English is all the numbers between 1 and 8, not including 1 and 8, okay? So this means does not include that number, okay? If I break it apart the other way and I write it with little brackets, this is all of the numbers including 1 and 8. Okay, so if you have a little brackets, that means you include the endpoints. If you have the little, you know, these guys, the parentheses, that means does not include. Okay, there's a rule that says you can never include infinity. Okay, so anytime you have an infinity, it's always got to be either a negative infinity like that, or at the end, you're going to have a positive infinity. Okay, you can also mix and match them. Okay, just because you didn't include one endpoint doesn't mean you have to do that to the other one. So if I write something like this, where I've got 2 and 5, this would mean it does include 2, but not 5. Okay, and then vice versa, right? If I did this 2 and 5, this would not include 2, but will include 5 here. All right. I know for some people, the notation for this is a little tricky. Here's my little way of thinking about it, doing this, okay, is we used to play softball, but this would work for soccer if you're a soccer person, whatever. So if you think about like this is a backstop, or this is a backstop, if you're like launching balls at this thing, they're going to hit and then they just kind of roll away from it, okay? So no matter what you do, like you've got a number here and you're tossing it at this parentheses, it just kind of slides off. So it doesn't get to include that endpoint. Right? If you have somebody who just throws the ball and it just kind of lands there and sits forlornly next to the backstop, well, that's included, but nothing's ever going to stick. Whereas if you throw balls here and they get hit, they're just going to drop straight down. Okay, and get hit with, get stuck at the bottom. Okay, so if I got like a 5 that I want to include, I throw the 5 here, it just drops, and again, we're just including it. Okay, and if it doesn't quite make it, that's okay. It's just going to lay there and be included. Okay, so that's just how I think about it. But you know, you're welcome to come up with other ways of visualizing this. I encourage you guys to do that, and you know, that's what interval notation looks like. All right. So when we've got this, right, what we're trying to say here is like, well, we got fractions, and we really would prefer that we didn't have a 0 on the bottom. Okay. So when we're looking at problems like this, we want the bottom should not be 0. Okay. I doubt any math teachers will watch this ever, but if they ever did, they're going to yell at me because they don't want you to say the bottom. Like, we taught you this word for a reason. We taught you the word denominator to say the bottom of the fraction. Use the right word. So there it is. The denominator is not 0. Okay. So if I'm looking at part A here, when is the denominator going to be 0? Well, let's find out where that is. Oh, x equals 9. Now, I know you could look at that and just write it down, but I guarantee you, these are not going to be quite so easy for your whole life. Okay, they're going to get more complicated. So that's why I'm just in the habit of solving for it. Okay, because it gives you a method. You can always use this. It's never going to make you wrong. And I like to remember fewer things. So how do I write this in an interval notation? Well, this is all the numbers except 9. And quite frankly, if we were in a face-to-face class and you wrote this down for me, I would mark you right because you've demonstrated you know exactly what we're talking about. I'd like you to write the nice notation, but let's get the understanding first, then we can work on the notation. But since we have a computer, we have to do them both. All right, so all the numbers up to 9. So that is all the numbers up to 9. Okay, and then we skip it, we skip 9, and we get all the numbers that are bigger than 9. So this is saying all the numbers up to 9, not including, and then 9, not including 9, and all the numbers that are bigger. And we put a little U here as a union. We say it's either in this one or it's in that one. Okay, so this is the way of saying all the negative numbers up to 9. We're skipping 9, and then from 9 onwards. Okay, so that's what this domain would look like in interval notation. All right, so we're going to have, see, they even give us, right, negative infinity, and then 9. And then they give us a little, where's my union? Oh, there it is. Okay. And then 9 off to positive infinity. Okay. So they give us all the tools to do this. Okay. So what about this one? There's a couple of points it can't have, right? For part B, you have x squared minus 9. Well, we can solve, right? Set that equal to 0. So that's x plus 3, x minus 3 is equal to 9. Or x plus 3, x minus 3 is equal to 0. And then we're going to do something called the zero factor principle, right? Interesting choice of way we're doing this. If I have two numbers and I say, if I multiply these two numbers and they multiply out to 12, can you guess what these two numbers are? And there's a lot of fun face-to-face because people are like, 3 and 4. Like, no, those weren't the numbers I was thinking of. How about 6 and 2? No, those weren't the numbers I was thinking of. How about 1 and 12? No, those weren't the numbers I was thinking of. 24 and a half? No, that wasn't the number I was thinking of. How about 1 over the square root of 7 and 12 square roots of 7? Did you guess that one? I know that was next, right? That was the next one you were going to do to get 12. So the point here is that if they're equal to 12, there's a lot of numbers you could guess to see if it's equal. If I've got two numbers and they multiply out to be 0, could you guess one of the numbers? Well, 0 times, I don't know, I don't even want to guess. One of them is 0. Yeah, that's it. Or the other one is 0. Yep, those are the guesses. So either the first one is 0 or the second one is 0, and we're going to use that here. Okay, so we say either the first one is 0 or the second one is 0. All right, this is called the zero factor principle. So we get x is equal to 3 or x is equal to negative 3. Those are the choices. Okay, so if x is either of these numbers, then we get a 0 on the bottom here, and we don't want that. So when I write down the interval notation, we're excluding these two numbers, right? We're saying everything except for those. Okay, so our values here, right? Let's write them in order. So our interval notation is going to be negative infinity up to negative 3. Then we're going to skip over negative 3 and go up to positive 3. And then we're going to skip over 3 and go all the way up to infinity. Okay. So again, if we were in face-to-face and you wrote down all numbers except 3 and negative 3, I'd be very happy with you. But here's where we have this. And then in later classes, you decide, hey, I love math. This is great. I should take, several more semesters of this. The other way, you'll learn this a little bit later. You'll say, well, it's the real numbers except for negative 3 and positive 3. I'm trying to write these in curly braces. I teach my students this method too, because if they want to write that, I don't have a problem with it. But we are constrained by the book that says you shall write it this way. So we're going to practice writing it this way. But I will tell you that in other classes and later on, you don't have to keep this. I mean, everything up to calculus, you're doing this. But after that, they teach you some other ways. All right, domain and interval notation. We have negative infinity up to negative 3. Union negative 3. Oops, I need a little one of these guys. Negative 3 up to 3. Union 3 up to positive infinity. And that's our interval notation for this thing. All right, it's delightful. All right, this next one, okay, just to finish this out, okay, we have x squared plus 9. Okay. Now, I'm not sure when we're going to get to the graphing of this thing, but that's one of the ways I would show you how to do this, is to graph it. But there's no numbers. I could square and add to 9, because if I square it, it's going to be positive. Right? 0 at the lowest, but it's going to be positive. And we're going to add a positive number to 9. Is it possible to get 0? I don't think it is, right? So this one is, the domain is just all the numbers. Okay, so this is kind of a trick question. So there's no numbers that are going to give me a 0. So the answer is all numbers. And in this notation, right, that's what that means, all real numbers. I'm still trying to make this fancy R like I had up here. I did a bad job. Okay, yeah, that's good. In interval notation, we have to say, well, that's all the numbers between negative infinity and positive infinity. And that's how you write all real numbers in interval notation. So that's what we're stuck with. Okay, that's what we're stuck with, is all real numbers this way. All right, so we'll check this one off. Okay, and move to the next one. All right, so this thing, oh, this is a good one. Actually, this is a really good problem. Okay, so we have y of t is equal to the square root of 36 minus t. So with these, this has to be greater than or equal to 0. Okay, and technically you would want to set it up like this. All right, you might be a little intimidated by this symbol. So here's another way to do this. Okay, 36 minus t equals 0. So what do we get? We get 36 is equal to t. Okay, but we have to remember that this was really what we wanted to write. So we have to see what's going to happen here. Okay, so what does my t have to be a bigger number than 0 or a smaller number than 0? Okay, so we need what they call test points. So here's my 36, and then we have to put t on either side to see what's going to happen. So pick your favorite number that happens to be smaller than 36. You can pick 35. You can pick 0. is 36 minus 0 going to work? Like, yes, 36 minus 0 is going to work. So t is less than 36. That's going to be just fine. Pick your favorite number that's bigger than 36. 37 looks like a good number. If I say 36 minus 37, right, that's going to be a negative number. That's not going to work inside of our square root. So 37, like, no, I don't like that. So this is called test point method. Test point. Or we could do this, right? We could do this. We could say, well, we could subtract 36 from both sides and have negative t is greater than or equal to negative 36. And then there's a rule that talks about when you multiply through by a negative 1, we have to change the signs, okay? So this is going to be t, but since I multiply by a negative, we have to change the sign here, okay? So we got the same answer either way we did this. Okay, t has to be less than 36. Can it be equal? Well, if we plug 36 in here, is the square root of 0 something? Is that something we can work with? Yeah, the square root of 0 is 0. So this is okay. We can include 36. So we're looking at this interval here, right? We have negative infinity here up to 36. And since we can include it, we use the square bracket. Okay. What about this one? What about w of t is equal to the square root of t minus 36? This one's a little bit easier to see, especially since we've done this one, right? If I pick numbers that are 36 or bigger, this will be just fine. But if we pick numbers that are smaller than 36, like 35, then we're going to have negative numbers here. So it's not going to work. So t has to be bigger than 36. But again, it can include 36. That's what this little equal sign here means, is you can include it. So we're going to say 36 off to infinity. Okay? Now, let's look at the third one here. This is z of t, 1 over square root of 36 minus t. So in this case, you might be tempted to say, well, that's negative infinity up to 36. What if I put 36 in here? Then we get a 0, don't we? And that's not going to work. So for this one, we have to exclude the 36 and leave it as that kind of an interval. Okay, so this shows you all the, well, not all, but it shows you a lot of the different types of what could happen here. Okay, so let's see, interval notation here, right, is going to be, we can go up to 36, that's fine. So our negative infinity up to 36. Oops, let's fill in all the empty boxes, fine. This one is going to be, oops, this is going to be 36 up to infinity. And this one, right, this was going to be this guy, right? Couldn't include either one of them. So it's going to be negative infinity up to 36, but not including. So that's what the little thing here means. All right, so all good. Okay. 2 more, promise. Okay, actually this is the same problem, right? Except for the odd roots. Can you take the fifth root, right, of a number, of a negative number? So if you take even roots, okay, if you take square roots or fourth roots or sixth roots, this isn't going to work. But if I came up and I said, can I come up with a way, can I get 3 numbers that if I multiply them together, I get negative 8? Sure, right? So when you take the cube root of or fifth root, or anytime you have an odd number here, okay? So 3, 5, 7, 9, whatever, okay? It's okay to have negative numbers as your answer. right? So if I want the fifth root of x plus 5, like, since we could take the fifth root of negative numbers, I'm okay with that. It's going to work. Any number I put in there is going to be just fine. Okay. So k of x, all numbers will work. And do you remember how we said all numbers inside of interval notation? Right? We did this, right? Negative infinity to positive infinity. Well, what if I turned it around? Like, I don't care. All negative numbers will work. All right. So m of x is all numbers work. So this is still negative infinity to positive infinity. All right. Now for n of x, okay, there's one number that won't work, right? And that's if I put 5 in here. So if the bottom happens to be equal to 5, so I don't want 5. Okay. So it's all numbers except for 5. And the way we write that in interval notation is negative infinity up to 5, skipping over 5 up to positive infinity. All right. So this one is a little bit tricky, but anytime you see this is an odd number here, then there isn't a domain problem, unless it's in a fraction, because then fractions bring their own problems, don't they? So interval and domain. Oh, you're going to make me write this out? Yes, you are. Right. Same thing here, right? Negative infinity, positive infinity. Okay. Now this one, a little bit different, right? We have negative infinity up to 5, skipping over 5. All right. And then we need more. 5 up to positive infinity. All right. Very good. Right. Skipping it over. All right. All right. Use the graph to answer the following. Okay. So here they're going to have a lot of, I'll put 1 of 9. It's going to be here for a while. Okay. So remember what function notation says, right? So if I want to do f of 0, this is the same thing of saying, well, if x equals 0, then what's my y value? All right, that's what this is saying. So f of 0, well, when x is 0, it looks like so is y. All right. No, this one they let me do it this way. Fine. All right. Oh, but they're still going to make me scroll down. Thanks. Okay. So this part, right? When x is 4, what's y? Okay, so f of 4. Right? So we'll go over here. 1, 2, 3, 4. Y value looks like it's 2. All right. Find all x for which f of x is equal to negative 1. Because it's possible, right? It's possible we get more than one value for this. Because we could have a whole bunch of things that do this. So where are we as far as x equals negative 1, right? What are the choices I have for all my x's that are going to give me this y value? And it looks like we've got one here. So x could be negative 1. That's 1 point. X could be 1. That would be another point that gives me a negative. And then x could be 3. And that would give me another one. So we have 3 spots where the function crosses this line. Negative 1, positive 1, and 3. All right. So we have okay, so we have negative 1, positive 1, or 3. Right. Very good. Find all x for which x equals negative 4. which f of x equals -4 rather. So again, we have to go back up to here. What are we looking for? -4. And it looks like, see this circle here, this closed circle, that means we include the value. So if I had a point, if I had a graph that looked like this, you know, here's 4, -4, that's included. However, if we had a graph that looks something like this with an open dot, this would not be included. Okay, so if they ask me like, what's the value here? The function is not defined. There is no value here. Okay, it looks like it's going somewhere. There's like, you could figure something out, and you will. Calculus, that's called a limit. That's a couple of years away right now. But so we have a way of talking mathematically about this. But right now, the actual value, it's undefined. This one is fine. It's got a closed dot. And for me, here, I always think about it this way because I had a teacher that his hardest problems were always ants crawling on something, ants crawling on a thing. So I always think like when they get to the end and you stepped on them, like there's a little dot that's there. Or if you tried to step on it but you missed, then you know there's a spot where you missed. Forever ashamed. Okay. So values for x equaling -4. Here we have 2. We have a -2 and a +2. Both of those numbers will give us f of -4. F of those numbers will both be -4. -2, comma, +2. It's very similar to the parentheses versus the brackets. Okay. Determine the x-intercepts. So x-intercept, this is where, all right, I always have to think about it this way. I'm going to guess that you've been tortured with that for more years than you care to imagine. Okay. And this would be the slope. This should be your y-intercept, right? That's what they drill into you, is this your y-intercept. So if x equals 0, then y equals, right? If x equals 0, then y equals b. This is your y-intercept. And all intercept means is that the variables take turns being 0. So your x-intercept must be when y is equal to 0, and then x is, we have to figure that out. Okay, so with intercepts, if they don't mention which one is which, just think to yourself, both of the variables get to take turns being 0. We'll let one equal 0, solve for the other. Let the other one equal 0, solve for that one. Okay, let this one equal 0, solve for that. This one equals 0, solve for that. Okay, they just take turns being 0. That's all there is to it. Okay, so x-intercepts, right? That is when y is equal to 0. That's on this line here. So it looks like 0 is one of those points, and then the 3 point, I don't know. Let's see if they give us a choice here. Oh, there are two. There are 2 x-intercepts. And they didn't make us name them. Okay, good. Because I have students that used to do that to me too. I typed out my graphs on Excel, and for people who are like reasonable at Excel, you realize like nothing ever quite lines up. They would take out a ruler. It's like, it's 3.01. Like, it's 3. I'm not trying to trick you. Okay, I just suck at Excel. So enter the x-intercepts in order and approximate the 1 decimal place. Fine. Now they're going to make us do it. All right. Now, what's my, well, that part's easy. It's y 0. So we got to figure this out, right? We have to look at this and say, well, approximated to 1 decimal place. I think that's 3.3. Okay. You said it was 3.2. I don't know if I could argue with you, but I think it's 3.3. All right. Hopefully they won't get mad at us. Hey, look at that. They were nice. Okay. Determine your y-intercept. If it's a function, there will only be one y-intercept, right? Because it's, where do they cross this vertical line here? One place, right there. Okay, just the one place. So that is 0, 0. Notice that all these are points. Okay, and I know it's confusing interval notation versus an ordered pair. I know, but it's kind of the context of what's going on here. Okay, domain of f. What are all the legal values of f? Right, all the legal values of x, rather. What are all the legal values of x? So I don't have a value right at -3. Starts at x equals -2. Then I have a value. If this was an open circle, then I'd need a parentheses here. But as it is, right, as it is, we're going to say, well, we can include -2. And what's the biggest x we have a value for? Well, it seems like once it gets to here, it says that it just keeps going, right? So what we're going to do is say that this was -2, and then it just keeps going. So that's what we're going to say is our domain. What do I want? I want, nope. Yep, this one. Remember the bracket, you can never put a bracket next to an infinity. Okay. It means like you're treating it really as a number, and you don't want to do that. Now, what's the range? All right, this is all the legal values of y. And it looked like the smallest value for y we got was -4, twice. And that went up to 0, but actually it keeps going, doesn't it? It goes up all the way to 2, but this never gets any bigger. So we're going from -4 included up to 2 included. Okay. So we're going to go here. We're going to say we're including both of these. So we have -4 up to 2. They're both included. That's fine. And then we'll see. Right? That looks pretty good. All right. So it's not so bad. I like the graph problems. Okay, because a lot of times we get information off of a graph, and we need to be able. It's still a 21st century skill, so I think we should reinforce this of being able to read graphs and do it well. Okay, but hopefully that gives you some chances to get through the last bit of the homework here. Hopefully you were following along and doing it that way, and I went slow enough that you guys could do that. But that's all I really have for us tonight. And I think next time, I don't have my syllabus up. I don't want to take the risk of exposing anybody. But we're going to, whatever week 3 says, we'll start with that. And I will just double check our Alex to make sure we're doing that. If you're stuck somewhere on either the Alex or the homework, you can either drop me an email or you can show up to office hours. Okay, you can ask a question here, that's fine. Okay, but we'll start off on week 3 next time, and I think we'll be okay. All right. So I'm going to stop recording.